Let's first solve a higher order ODE analytically, and we will use the simple higher ODE second order linear ODE to talk about how to solve it analytically. Okay, so the example is homogeneous second order system, ODE system, and this is a linear system with constant coefficient. Okay, so we can write this second order ODE as y double prime, that is the highest order, plus a y prime plus vy. And this is a homogeneous second order ODE, so the forcing function will be equals to 0. Okay, and you know that for constant coefficient homogeneous ODE, the solution we will guess with exponential function. So we assume the solution form is look like exponential function, so e to the lambda x. Then we can put this form back into our second order ODE, where the y double prime will be equals to lambda squared e to the lambda x, y prime equals lambda e to the lambda x, y is equals to e to the lambda x. Okay, you can input each term to replace the higher order here. So we get lambda squared e to the lambda x plus lambda e to the lambda x plus, there is a coefficient a, there is b, e to the lambda x equals to 0. And you know that the exponential function won't be 0, so we can cancel the exponential part from the left and the right, which is 0 on the right. So the left side will left a polynomial in the end, which is lambda squared plus a lambda plus b is equals to 0. So this is a second order polynomial. And this is also called the characteristic polynomial for a second order linear ODE. Okay, so this is characteristic polynomial. And then in order to solve analytically regarding this form, we need to get the root of lambda so that we know what is our solution form. And you know this is pretty easy. So the root of lambda will be equals to minus a plus minus a squared minus 4b divided by 2. And it really depends on what is the numbers, whether it's positive, negative, or 0 for the root square part, a squared minus 4b. Then we can see how the root look like and how the solution form look like. So we will talk, different scenarios, whether this part is positive, negative, or 0 in the following part. The general solution for this homogeneous second order linear ODE with constant coefficients is a linear combination of different linear independent solution, right? So it's a linear combination, which is, we can write as CIYIX. And we have only two linear independent solution, which is C1. Y1 we can write as e to the lambda 1x plus C2 e to the lambda 2x. And you know this lambda 1 and lambda 2 is equals to these equations, right? So the plus sign will be, so there the lambda 1 is equals to minus a plus a squared minus 4b divided by 2. if lambda 2 is equals to minus a plus, sorry, minus a squared minus 4b divided by 2. And that is general solution. And this general solution is strongly dependent on this root a squared minus 4b roots. So if we have a real root, which means, okay, real root. So this is for the part for a squared minus 4b. Okay, for the real root, which means the a squared minus 4b will be over 0. It's a positive number. Then the root square will be a real root. And one particular scenario you can think about will be a equals to 0, b is smaller than 0. So this is just one particular scenario. There can be many other scenarios. It's like a square has to be over 4b, right? So this lambda 1, 2 will be equals to plus minus the absolute number. And we can say this is represented by alpha. Okay, this is represented by alpha. Then how we write our final solution, this general solution by x will be equals to c1 e to the root square absolute number b x plus c2 e to the b x with a negative sign. Okay, and we can also write this as hyperbolic case. In some physical models, it's better to write as sine cosine form so that it's easier to plot. And we can write this C1 as we can write as e to the lambda x plus C2 e to the minus lambda x. It's just for a simple representation. Okay, and we can say that it's also equals to K1 times, so we just replace the constant, e to the lambda x minus e to the minus lambda x divided by 2 plus K2 e to the lambda x plus e to the minus lambda x divided by 2, where the C1 is equals to K1 plus K2 divided by 2, and C2 is equals to K1 minus K2 minus K1 divided by 2. So we are just trying to rewrite this exponential part with hyperbolic function. And this will be equals to K1 times think lambda x plus K2 cos lambda x. So in the plot, or if you know this function, you will imagine that it look like that. So you can imagine the physical meaning of that model you are investigating, but you know, represented by either the exponential part or the sine cosine part are both fine in this class scope. Okay, so that is for the real root. Then the next part we will talk about how about the negative root. Okay, so if my a squared minus 4b is smaller than 0, that means my roots of a squared minus 4b will be a complex conjugates. Okay. Then how we represent the general solutions. So let's, if that is a complex conjugate, we can write our lambda 1, 2 will be equals to lambda plus I beta plus minus. And you know this lambda alpha is equals to minus A over 2. The beta is equals to 1 over 2 A squared minus 4B with absolute number there. So this is when the first A squared is smaller than 4B, so the root is a complex conjugate. And you also know if we write our root, we can write our general solution by H x. So the general solution H, well, is still a linear combination of both linear independent solution, C1 y1 x plus C2 y2 x. And you know you C1 x will be e to the lambda 1x plus C2 e to the lambda 2x. And you know you lambda 1 and 2, which is C1 e to the lambda plus I beta x plus C2 e to the minus e to the lambda minus I beta x. So this is your general solutions. And we are also trying to write as a sine cosine way so that it's easier to imagine what is the physical model in the picture look like, okay? So e to the I beta x plus minus sign there will be equal to cosine beta x plus minus I sine beta x, okay? And in which, if you want to represent this cosine and the sine with the exponential part, you can get cosine beta x will be equals to e to the I beta x minus e to the minus I beta x divided by 2I. Sine beta x will be equals to, oh, sorry, this is sine part. So the cosine beta x will be equals to e to the I beta x plus e to the minus I beta x divided by 2. And then we can use this sine and the cosine beta x to represent our general solution here by using this form to represent our exponential part, okay? So the standard form of the solution can be also written as C1 e to the lambda 1x is equals to C1 e to the lambda x times e to the I beta x. And the e to the I beta x will be equals to this part, which is C1 e to the lambda x times cosine beta x plus I sine beta x. Similarly, you have the C1 e to the lambda 2x, C2 e to the lambda 2x, which is the second solutions. That is C2 e to the lambda x times e to the minus I beta x. That is C2 e to the lambda x times cosine beta x minus I sine beta x, okay? And then you can write, you can input this two form represented by the cosine and the sine into your original general solution by hx. By hx will be equals to e to the lambda x, because both of them have the e to the lambda x form, so we make it outside the equations. And C1 e to the I beta x plus C2 e to the minus I beta x. And we can just write as cosine sine form, which is e to the lambda x times k1 cosine beta x plus k2 sine beta x, where UK1 will be equals to C1 plus C2, UK2 will be equals to I times C1 minus C2. So in that sense, your general solution will be written as a cosine sine, this kind of form instead of the exponential part, okay? There is a third scenario, which instead of real roots, two distinguished real roots and two distinguished complex conjugates, we can also have just the one root, okay? The one roots look like, what if my a squared minus 4b squared equals to 0? That means you only have one root. Then we have only one root for the square of a squared minus 4b squared, right? That is basically 0. So then what is your alpha look like? Lambda look like? So lambda 1, 2 will be equals to minus a divided by 2. And you will only have one solution since you only have one lambda. Your solution will look like y1, 2. By solving this analytical solution, you only get one root, which is minus a over 2x. Okay, so only one solution. However, in the previous part, we also mentioned that for higher order ODE, n order ODE, you need to have n linear independent solutions, which will consult the whole solution set of your homogeneous solution. Right now, this is a second order linear ODE, but you only have one independent solutions. Then we need another independent solution to construct the whole solution set of this homogeneous general solutions. So to find the second solution, or you can say the second linear independent solution, y2, we will apply a method which is called reduction of order. Reduction of order.